Good day viewers, this is a Science Demystifier. Welcome to my YouTube channel. In today's lesson, I will be taking you through an important topic in chemistry, and that is atomic structure. So I will single out a part of this topic which students find difficult to comprehend, and that is the Bohr's quantum theory. Now let's not forget that before the Bohr's quantum theory, there were other theories which helped in the development of the atomic structure, starting with the Dalton's atomic theory, J.J. Thomson's plumb-unipody model, Rutherford's nuclear model, and now the Bohr's quantum theory. Now, to explain the black body radiation observed by Maxwell Planck, and also Einstein's idea of photoelectric emission, Bohr's used their ideas to explain his observation about the hydrogen spectrum. So it was from there that Bohr's developed his quantum theory of the atom. I'll be back shortly. Alright, welcome back. Sequel to Rutherford's nuclear model of the atom, there were questions that Bohr raised about Rutherford's atom, and the answers he provided to those questions was what that paved way for the quantum theory of the atom. Number one, Rutherford said that an atom is like the solar system, having a nuclear center, that is a core of positive charges, around which are electrons. The electrons orbit around the nucleus, just like the 9 planets orbit around the sun. Now, following Maxwell Planck's idea of the atom, that atoms emit energy. These energies emitted by atoms were believed to be coming from the accelerating charge, which is the electron. Now, if an electron is in one stationary state and it emits energy, it means that the energy of the electron at some point will get exhausted. And when the energy gets exhausted, the atom will definitely collapse into the nucleus, will fall into the nuclear center of the atom and stop existing. But that is not the case. We see electrons constantly revolve around the nucleus. Now, it means that the energy of an electron is conserved, contrary to what was thought to be. Now, Maxwell Planck, Neil Bohr answered the question that he raised. He said, why an electron is still in orbit or in stationary state, that it does not emit radiation, it does not emit energy, that an electron will only emit energy if it jumps from one energy level to another energy level. The energy level transition might be an ascension or descension, whichever one, and that is what that gave rise to the absorption and emission spectrum. Now, without wasting much of your time, let us look at the second question that Neil Bohr raised about the atom. He spoke about the system of force that keeps an electron in equilibrium, that is, in its stationary state. A charge like an electron, remember the electron is negatively charged, cannot be moving around a positively charged nucleus without a force of attraction emanating from the nucleus, pulling it inwards. Now remember, there is what we call the Columbus force of attraction that exists between two unlike charges. So since the nucleus is positively charged due to protons that emit, and then the electrons that orbit around this are negatively charged, then there must be a Columbus force of attraction which tends to pull the electron from the orbit towards the nuclear center. But it is seen that the electrons do not move towards the nuclear center. It is always kept in orbit So what system of force keeps the electron in orbit? So he also answered this question, that the centripetal force, which is the force that drags an object from orbit towards the center, is balanced by a centrifugal force, which is the one that emanates from the center to the orbit. The force of attraction pulling it towards the center is the Columbus force of attraction, which is given by the law of electrostatic field. Then the one that tries to throw it out of orbit is given by the centrifugal force, which emanates from the center. So without wasting much of your time, let us go to the board and demystify the process. So from there, we'll be able to obtain an equation for the radius of the atom, from where we'll understand the quantization principles. So let's go to the board and do the needful. Okay, welcome back. Now we're going to see a pictorial representation of these two balanced forces that keeps electrons in orbit. Supposing you have an atom, this is an atom, and this is the nuclear center of the atom, okay? And now here is an electron moving round or revolving around the nucleus. So there exists a force that emanates from the center of the atom, which is the nuclear center, towards the electron. So this force that emanates from the central part to the outside is what is called centrifugal force. And centrifugal force is given by the formula mv squared over r. Then another force now exists from the outside, which is the orbit, towards the center, which is the nucleus. And that force is brought about by the Columbus force of attraction in electrostatic field. So the formula for the Columbus force of attraction is Ze squared over 4 pi epsilon naught r squared. Those of you that have done something on electric field will understand this is a very conversant formula. This is a formula that shows the force that pulls unlike charges together in an electrostatic field. Don't forget that Z in this formula represents the number of nuclear charges. Like in a nucleus, we may have 1 proton, 2 protons, 3 protons. So Z is an integral value of the number of nuclear charges that we have. So the E here represents the quantity of charge present in the atom. So remember that in an atom, if you have 1 proton, then we have 1 electron. If you have 2 protons, then we have 2 electrons. So that's why we have 2 E's. So the E times C will give you E squared. Then divided by 4 pi epsilon naught r squared. So at this point, I can cancel out my r. So when I cancel out the r with the r squared, I have 1 r left. Okay? So making V squared the subject of the formula, we now have Ze squared over 4 pi epsilon naught, which is this epsilon is called permittivity in free space. So epsilon naught then mr. So let me leave this as equation 1. Now where am I heading to? I'm heading towards deriving what we call the Bohr's radius. Okay? Because when we get the radius and we discover that the radius of an atom is quantized, that is, it is discreted, it gives us an idea of the Bohr's quantum theory, which suggests that electrons exist in certain allowed orbits or stationary states. So once we get to that place, you will see that that was the clear picture of what Bohr was trying to paint, and that was what led to his quantum model of the atom. So I'll be back shortly. Alright, now let us look at the angular momentum of an electron. An electron being a particle of mass m, and it is revolving around the nucleus with a velocity v, then that particle must have a momentum. So he opined that the angular momentum of an electron is quantized by a discrete value which he gave the formula as NH over 2 pi. So MVs are angular momentum of an electron. I don't know if you can see it. MVR, angular momentum of an electron, he said, is quantized by a discrete value, which he says NH over 2 pi. This N is the quantum number of the shell in question. This H is called the Planck's constant. And then here is the mass of the electron, the mass of the charge. This is the velocity of the electron. So from here, I want us to make V the subject of the formula. We had it somewhere. So making V the subject of the formula, we have V is equal to what? NH over 2 pi mr. Now I want us to take the square of both sides. When we square both sides, we have V squared equals N squared H squared over 4 pi squared M squared R squared. Okay, so that is what we are going to produce. So let us call this one equation 2. Now, having produced another V squared, remember in equation 1 we got a value for V squared. So we are going to equate equation 1 and equation 2. I'll be back shortly. Welcome back. Now, remember in our equation 1 we got V squared to be equal to what? ZE squared over 4 pi epsilon naught R. Okay? This was what we produced in equation 1. So in equation 2, we got our V squared to be equal to N squared A squared over 4 pi squared epsilon naught. Okay, no, there's no epsilon there. 4 pi squared I think M squared R squared. Okay, so we are going to equate 1 and 2. So when we equate 1 and 2, we have ZE squared over 4 pi epsilon naught R squared. I believe you can see it clearly from there. That's equal to N squared A squared over 4 pi squared M squared R squared. So here we can cancel like terms. For example, we can do away with the R. Sorry, this is only 1 R. So this R will cancel this one to leave us with 1 R. 4 will cancel 4. Pi will cancel 1 pi. So we have only 1 pi remaining. Then let us write what is remaining. So we have ZE squared over epsilon naught. And that's equal to N squared A squared over M over pi M squared then R. So if I cross multiply, I'll have ZE squared pi M squared R. That's equal to N squared epsilon naught H squared. Okay? So from here, I can now make R the subject of the formula. I believe you can see the solvents clearly. So can you see the solvents now? So we started from here, this is equation 1. And here, this is equation 2. And now here we equated 1 and 2. So we can make R here the subject of the formula. So here we are cross multiplying. So we can make R here the subject of the formula. So making R the subject of the formula will give us an idea of what the Bohr's radius is all about. Now let us equate 1 and 2. So we have done that already. And we have ZE squared, we have pi, we have M squared, we have R. And that is equal to, okay, let me bring it down a little bit so you can see ZE squared pi M squared R. And that's equal to N squared epsilon naught and H squared. So from here we can make R the subject of the formula. So R will now be equal to N squared epsilon naught squared H square divided by ZE square pi M square, right? So this is the formula for obtaining the Bohr's radius. So to make the equation shorter, the quantity E naught H square over ZE square pi M square was given as 0.052. So they've already calculated everything, assuming that Z is equal to 1. Assuming that that's for an atom of hydrogen, the value of Z here is equal to 1. So when you substitute and put the permittivity in free space, which has also a constant value, you should be able to get plus constant is also a constant. So almost everything here is a constant. So when you put all the constants together, you arrive at this value 0.0529. Okay? So that means my Bohr's radius will now be reduced to m squared times 0.0529. Okay? Now you discover that this n here is the quantum number of the shell where the electron is residing. So for each of the shells, the value of n defines a particular radius. Do you get it now? So if, for example, for the Kersh shell, the value of n is equal to 1, when you substitute, it will give you a particular value for the radius. Remember, if you have concentric circles, assuming that these are shells, and you have to measure the radius of each of these shells from the center, you start to be a variation. So the radius of this first shell will not be the same as the radius of the second shell, and the radius of the third shell will not be the same as the radius of the second shell. So the radius keeps increasing as the quantum number increases. So that gives an idea that electrons exist in certain energy states or stationary states. They are not in the same energy level, okay? So this is an idea of what the Bohr's radius is all about. So if n is equal to 1, or n is equal to 2, or n is equal to 3, you can get the corresponding value of R, which defines the Bohr's radius of the atom. So because the radius of an atom is not a single value, it varies depending on the value n, and that value n is what that defines the principal quantum number of the shells. That means the atom has energy levels or stationary states. So this is what that forms the basis of Bohr's quantum theory. In my next lesson, I will be showing us how to obtain the one that Sommerfeld did, explaining the fine structures that we observe in the spectrum of hydrogen, because each energy emitted in an atom has a line that it will draw on the electromagnetic spectrum. So each of these lines were seen in different regions of the electromagnetic spectrum. Some were viewed in the Baumann, the Lyman, the bracket, the Pfund. There were a lot of lines that were viewed in all these regions. Okay, but Bohr's quantum theory still suffered some shortfalls, which Sommerfeld and other scientists were able to demystify. So that is the much we can take for today's lesson. If you are just watching me for the first time on this channel, please don't leave without hitting the subscribe button. And if you're an old subscriber, please, if there's anything you want us to do for you, if there's any topic in chemistry you want us to demystify for you, please don't hesitate to do that in the comment section. Feel free to make your contributions. Feel free to contact the Science Demystifier for your tutorials. Anywhere, online, physical, we are there to assist you. So thanks for watching. See you in my next video.